So in our last lecture, we have studied the equations for calculating the frequency spectrum of a periodic signal. And we have studied the trigonometric form as well as the exponential form. Now what we are going to do in this particular session is to take a specific periodic signal and analytically find its frequency spectrum and also write a program to calculate the frequency spectrum. That is what we are going to do. Alright, so let us start. Now for illustration we are going to consider a sawtooth signal. So let us first of all plot it and see how it looks like. So I have showed only 3 cycles of the waveform here, but as you know the periodic signals exist right from minus infinity time value minus infinity right up to plus infinity. But for obvious reasons I have plotted only a few cycles here. Now this particular sawtooth signal has a time period which is 2 pi seconds and it has got a maximum amplitude which is equal to 10. In that case, first what we do is we write the equation for xt as a function of t, and the equation that we write is valid over one time period. So clearly it is an equation for a straight line, and the slope of this straight line will be 10 divided by 2 pi. That will be the slope of the straight line, and it is passing through the origin starting from here. So clearly there will be no intercept. So therefore the equation for xt is 10 by 2 pi, that is the slope, multiplied by t, that is time. Okay. Now first what we are going to do is to calculate the DC component for this waveform. So that is calculated like this as we studied last time. You integrate over one time period, integrate xt itself over one time period and divide it by the time period. So what we need to do is to substitute for xt from here and then solve the integral. But since this is a straight line, we can also directly solve it geometrically without evaluating the integral. So that will be area under the curve over one time period divided by the time period. So area is what? Half the base into height. So 0.5 multiplied by base, which is 2 pi, 0.5 into 2 pi into height, that is 10. And this divided by t, which in this case is 2 pi seconds. So 2 pi cancels and 0.5 into 10 will give you 5. So the DC component, which is A naught, also equal to C naught, also equal to X naught of the exponential Fourier series, that is equal to 5. Next, we want to calculate the fundamental component, second harmonic, etc. That means what is the amplitude of the fundamental, what is the phase of the fundamental, etc. That is the frequency spectrum. So we want to calculate that. So first of all, let us see what is our omega naught, that is the fundamental frequency in radians per second. So that is 2 pi divided by t, and t itself is equal to 2 pi. This is 2 pi divided by 2 pi, so that is equal to 1. So that is your omega naught, which means that when you calculate the frequency spectrum for various values of n equal to 1 will mean omega naught, n equal to 2 will mean second harmonic, 2 omega naught, and so on. Okay. So let us see the trigonometric form of the continuous time Fourier series, which we studied last time. So xt is a naught, which we have already calculated, and then y, now we need to calculate the expressions for an and bn. So for an it is 2 by t integral 0 to t xt cos of n omega naught t, and if you substitute for xt here and evaluate this integral, you can verify this yourself by substituting. You will find that an turns out to be equal to 0. Then if you calculate bn by using this equation after substituting for xt from here, then you will find that you will get the expression which is minus 10 upon n pi. So this means that as n goes on increasing, as the frequency component has a higher and higher value, the amplitude goes on decreasing. So this means xt equal to, first of all, a naught, which is equal to 5, then n equal to 1, so you will get minus 10 by pi. sine of t, because omega naught is 1 and n is 1. So that is sine of t. Then minus 10 upon 2 pi. Note that n equal to 2. So this is sine 2t. Then minus 10 upon 3 pi sine 3t, etc. So this is your xt. And you have essentially obtained the amplitude of various frequency components. What about the phase? So if you take sine as the reference, clearly the phase is 180 degrees for each of the components. That is same, because there is no cosine component at all. However, we can rewrite this somewhat differently by using the cosine as a reference function also, and both equations will be identical. So if I convert minus sine t into cos, then I have to write plus cos of t plus pi by 2. So each sign is converted into cosine, and each negative sign gets converted to pi by 2 radians. So in terms of cosine, your xt is given like this. So you can see your amplitude spectrum. How will it look like? DC component is 5, then n equal to 1, that is fundamental, that is 10 by pi. Then second harmonic, that is 10 by 2 pi. Third harmonic, that is 10 by 3 pi, and so on. And for each of these frequency components, the phase is same, that is pi by 2 everywhere. So it will be a simple matter to now plot this line spectrum. So what we are now going to do, so this problem solving that we have done is by using the analytic method. We have the expressions for A naught, AN and BN. We have substituted and obtained our equation, and therefore we can plot the frequency spectrum. Now what we are going to do is to study the program by the help of which we will be able to plot the frequency spectrum. Okay. Now understand that your xn, what we are going to do in this program is to use the exponential form of Fourier series, because understand this is somewhat easier to compute since you have to solve only one integral. Otherwise you have to calculate for an, bn and so on. So we are going to do this. And xt, as we know, is given as 10t divided by 2 pi. Now when we write a program, clearly xt is going to be a discretized version. It will be a digital representation of xt. So since it will contain number of samples, we need to know how to do the integration. So that is in the digital form we want to do this. So to illustrate this, let me show you this waveform. So this waveform is some arbitrary waveform. I am not saying that it is corresponding to this. I am just trying to explain in general how to calculate the integral when your waveform is represented by discrete samples rather than the continuous values. Understand that in a digital computer, everything is going to be represented by discrete samples. So this is the 0th sample. Then in this case, the sampling time is 0.5 seconds. So after the sampling time, this is the next sample. So when you evaluate the integral over so much time period, basically you are evaluating the area under this. What it means is that if you calculate the area of each rectangle and then add all these areas, you will get your integral. But since calculation for each area involves the same sampling time period, what you can do is you can first sum up all the samples and then multiply the sum by ts, and this way you can calculate the integral. So understand this, that integral is going to be calculated in this fashion. With this in mind, let us now try to see how to develop the program for plotting the frequency spectrum. So this is what we want to calculate. Xt is given by this. So first what we do is, first we write a function which will generate the sawtooth waveform. So how do we write that? Function xtts equal to sawtooth. So to represent sawtooth, I have just written saw here. Now t is the parameter which is passed from the main program to this function. So t is the input parameter, and that corresponds to the time period of whatever waveform that you are trying to generate. In this case, the sawtooth. These are the output parameters. So x is the signal itself, t is the time vector, various time values, and ts is the sampling time. These are all generated inside the function and they will be returned when the function is called by the main program. Alright. So first we define the sampling time, and for accurate calculation this has to be much smaller than the total time period of the waveform. So we choose it t divided by 1000. That is our sampling time. So then what we do, we define the time vector. So time vector is 0, increment of sampling time, that is ts, and the last value is t. Remember, we are going to plot this over one time period. So this is it. Then x is equal to 10 divided by t, that is the slope, multiplied by small t, that is the time vector. Don't confuse between the capital T and the small t. Capital T is the period of the waveform and small t is the time vector which is generating this waveform. So that is your x. So all these parameters for the output are now generated here, ts, t and x, and you can end the function. So this function is going to be called by the main program, and it will use the sawtooth function that it returns in order to compute the frequency spectrum. So the next part of the program will be the main program which will be using this function. So let us see what it is. So as usual, we clear the variables, clear the console, clear the figure, then define t equal to 2 pi. Remember, where this is the main program which is going to call the function, and this is the parameter which has to be passed to the function. So t is equal to 2 pi. And now you call the function. So these are all output parameters, x, t, ts. This is equal to saw t. So now x is available. So you first calculate the DC component by summing x multiplying by tc, which is the integral over one time period. Because x itself is defined over one time period. That is why I am saying that this is the area over one time period, and divide it by t and you will get your DC component and you can display it. Okay. Next you want to calculate xn. But before that, what we do is we plot this, that is this sawtooth function which has been returned, that we plot. So subplot 311. Now 311, because this is only part of the main program and we are also going to plot two more plots. So this is the first of it. So subplot 311, plot tx. So we are just plotting the sawtooth waveform, and these are the usual functions which are used for usual statements which are used for describing the graph itself. Okay. So when this part of the program is executed, you will find that the sawtooth wave is plotted. On the x-axis you have plotted time, and on the y-axis you have plotted the amplitude. It reaches a maximum value of 10 at time equal to 2 pi, which is 6 point something. You can do the calculation. Alright. So this is how the waveform xt looks like. Now you want to calculate the spectrum. DC component we have already calculated and it can be displayed, and you can convince yourself that it will be very close to 5. I am saying close to 5 because usually in all discrete calculation there will be some minor errors. So it may not be exactly equal to 5, but around that. Okay. Then next we write the program to calculate the complex coefficients. Now n equal to 1 to 10. Understand that when we obtain the frequency spectrum of a periodic signal, the number of frequencies actually extend to infinity. But obviously, for obvious reasons, we can plot only finite number of parts of the frequency spectrum. So in this case, we have chosen n equal to 1 to 10. You could choose n equal to 15, 20 or only 5, depends on what is your need. In this case, I am plotting 10 frequency spectrum coefficients. Omega naught that is 2 pi by t. Now for n equal to 1 to 10, so you go into this loop. So you first calculate the exponential function. Remember we had e raised to minus j omega naught n t. So its Matlab equivalent is exp minus I into omega naught into n into t, that is your e. Then you have to multiply it by xt. So x1 is calculated as x dot star e. Remember this is a sample by sample multiplication. So you can't use just x star e, otherwise it will consider it as a vector matrix multiplication, but we want point-wise multiplication. So we say x dot star e. Then we sum this. Understand that we have to integrate this. So we sum it and then multiply the sum by sampling time, that is ts. Then we also have to divide it by t. So you have got your complex coefficients now. So when you go through this loop once, you will calculate one coefficient. When it will go through it again, so this is n. So n equal to 1, it will generate x1. Then it will go back, it will make n equal to 2 and generate x2 and so on. So you now have all the complex coefficients that you need. And now what you need to do is to find the absolute value for plotting the amplitude spectrum, and you need to find the angle for plotting the phase spectrum. But before doing that, understand n equal to 1 to 10. Okay, so this was for the for loop. This was already defined, but anyway, this probably this was not necessary, but I have defined it again. And then n is equal to n star omega naught. Okay, understand? When n is equal to 1, then the frequency is omega naught. N equal to 2, it is 2 omega naught. So I have changed n to this. So basically the when you plot n on the x-axis, it is calibrated in terms of frequency. Okay. So now you need to plot. So what you do, subplot 312 is the second plot. Stem, now x is already available, you plot its absolute value, plot it, these are the usual. Then find the angle of x, which will allow you to compute the phase angles for various values of x, and then you plot that. So let us now see all the three plots together. This is your time domain xt. Okay, this is the amplitude spectrum. Remember we had seen it was 10 upon n pi. So as n goes on increasing, remember in this case n and n omega naught are same because omega naught is equal to 1. So this n equal to 1, also 1 radian per second, 2 radian per second, and so on. And if you recall, as n goes on increasing, this goes on decreasing, and you can actually verify its absolute values also. Understand that we have used the exponential form of Fourier series in this program. So actually it's a double-sided spectrum, but for convenience here we have plotted only half the side. The other side also can be plotted by some modification to the program, but understand that only positive side of the spectrum is plotted. And for amplitude spectrum, if you plot the negative side, it will be even function of frequency. Now phase spectrum, remember for each cosine value the phase angle was pi by 2. So that is what it is here. It is all constant for all values of frequency. So for omega naught equal to 1, it's pi by 2, omega naught equal to 2, it's pi by 2, and so on. So what we have done in this session is given an example of calculation of frequency spectrum of one particular periodic signal, in this case sawtooth. That's an illustration. So we have done it analytically, and we have also shown how to write a program. So it is hoped that once you have understood this, you will be able to do this for other periodic signals also. You will basically have to change the function for calculating the function for the given waveform. In this it is sawtooth, it could be a square waveform, pulse waveform, triangular waveform, and so on. So that's all in this particular session.